Okay, if we all are ready, I think the plan is that Andrew will update us on the progress that has been made on the MIG Weld testing.
Mm-hmm.
Then we can briefly talk about measurement of residual stresses on those samples, and then, of course, the main topic would be looking into the testing of case-hardened bolts. Uh,
Yep.
So if you agree to that, we can ask Andrew to take over and give us an update on the measurements.
Yep.
Sure. Okay.
Yeah, we can see your screen, Andrew. Yeah, thank you.
Perfect. Okay. Just give me 1 second. Okay. Everyone's able to see?
Yep.
Perfect. Okay. I'll just give a brief overview of the state of, or I guess the current state of the MIG welded samples that you've sent over. So we have gone through all of them and measured key dimensions as per our test plan that we've discussed. We did manufacture um, fixtures for cyclic loading as well as monotonic overloading. So
Uh-huh.
this is what it looks like here. We did complete on the 590 specimens. We've completed the static monotonic tests. So this is one example of the test here. So you can see the force displacement, and then you can see a video of kind of the failure mode. It's a through crack along the axes of the weld here, about 21 kilonewtons peak load. Um, so the important thing to kind of note here is the peak obviously is quite high. So we made sure that the fixture can
Uh-huh.
obviously withstand that loading. But this load is much higher than what we're doing with fatigue. We're loading what like below 2,000 newtons. So less than 10% of this is what
Mm.
causes the failures within the life ranges that were requested, or I guess actuation in the life ranges that were requested. Have looked at once the sample obviously tears apart, depending on the morphology of the fracture surface and the style of failure that occurs. This is one example of a through weld where we looked at looking at the area of the weld using an imaging technique, and then actually calculating the area of all the voids that were present in the face of the crack. This is a fatigue crack for this particular one, and then calculating the void fraction. So one thing that's immediately obvious is that there is some scatter in the fatigue data, and I'll go over that in the next slide. But the scatter is very much due to the size, the size of the I guess these voids, these void bubbles, and their proximity to the edge of the weld. Okay, so this particular sample has a large void on the right. Okay, and it's fairly close to it's a moderate distance away from the edge, and then there's also a large one to the left. So one would kind of estimate that that would have equal um, propensity or probability of failing on the right and the left almost simultaneously, and that's kind of what we observe. Depending on if it was a smaller weld, the initiation, or sorry, a smaller void in the weld, the initiation life will obviously change quite a bit. So I'll discuss that now quickly. These are the fatigue tests that we've run so far on the 590 material. So you can see load on the y-axis and life on the x-axis. Um, it's logarithmic scale on the x, just as conventionally someone would present a fatigue graph. One thing that's important here is that we're just looking at the total life here. So you can see there's some scatter. If we fit a trend line through the data that was not a run out, so we do have some tests that exceeded 1 million lives, which as per the test plan, that's considered an infinite life for this particular case. We also have characterized using an imaging technique, and I can discuss that in more detail if you'd like, but it'll be included in the test report. Once the crack reaches 2 millimeters in length, Then we calculate the life that's required to achieve that threshold of 2 millimeter crack length, and we find these data points here. So with the exception of this one outlier, and I'll kind of describe why that is in a little bit, they somewhat fit a linear line when you plot it on this linear log plot. So this is kind of the best fit of that particular data. The interesting thing to note is that both of these lines are parallel when you plot them like this, and the difference between the two is about a 12 times difference between the initiation life and the failure life. So that kind of holds true for most of the tests. So when we're looking for, or targeting an initiation life of the ones that were requested in the cycle regimes, the total life often is sometimes a run out test. So we did have a few runouts here, but we did, and that was at zero point 0.5 kilonewtons of maximum load. However, we did have one failure at 1 kilonewton of maximum load that the total failure or the final failure was at 984,000. So we do have some good resolution at the very end of let's say the domain of infinite life. So that's good. In the runout regime, we're characterizing that well. Due to COVID, obviously testing has been a little bit different than what we would conventionally do, not in terms of the procedure, just in terms of the efficiency. There's restrictions on timing of the university of when we can actually utilize the equipment. So a lot of planning is involved in making sure that the tests are running overnight and over the weekend so that we can get this done. Um, so I'll go to the next slide here. We've established the 5 load levels to achieve the various initiation lives that were required. So I believe it was 10,000, 40,000, 80,000, 200,000, and 400,000. So these are the windows of loads that were, or lives that we're looking at in the corresponding loads. So they're quite low. They're less than 10% of the failure load in a monotonic sense. So that just gives you a relative idea of what we're looking at. Once again, this is only for the 590 material. The load levels will change as you change the material, but more than likely it's going to be limited by either the has or the morphology of those voids near the edge of the weld. So I'll go
So where
forward to
did you
the
take the section? And you showed a section, right? Where did you take that section? Where you showed the void? It is
sure.
somewhere. It is
That's
somewhere in
the
the middle of the belt, or
So that's the failure surface. Eventually, we will do an actual section to calculate the area of the weld on one of the samples, but right now this is just the failure surface. So whatever plane the the actual weld failed on. So it's not exactly in plane with the top member. It's somewhat in plane. It's what you would expect, kind of the maximum plane of critical stress would be in the weld itself. It's a slight oblique angle. Hopefully that gives you the right answer for what you're looking
okay,
for.
got it. Okay, yeah. So when two pieces got separated, you took a view of that.
Correct, yes. Otherwise it would
Okay,
be a destructive test. So we will do one of those and we will section the weld and calculate all of those dimensional properties that you want. But in order to get
okay,
this type of weld void fraction for all of the samples, it makes the most amount of sense to calculate it on the plane of failure. Okay, so now
okay.
just moving forward. So just to give you an idea of kind of what the fatigue test looks like, this is for a test where 4,000 newtons was the maximum load. So I will just pause this for a second here. If you give me 1 second. So what we're looking at here is a plot that will show we're capturing images to monitor the crack length at the peak load, and then we have this interval here where we're capturing kind of a mid-cycle or one cycle, and this was at an initiation life of 3,201 cycles. That's what you see here. So not exactly within the window, but this was one of the first tests that we've performed, and you can see. I'll fast forward a little bit here.
So in this case, the weld fractured or where the crack initiated, on the weld or the base material?
So this one is the weld.
Looks
It's right at the
okay.
edge of the
So
weld here.
So
So
on this thickness combination, all your cracks were on the weld, is it?
excellent question. So it depends on the load amplitude. If you have a high
Okay.
load amplitude, or a
Uh-huh.
high shear stress or high stress at the root or the notch of the weld, you are gonna
Uh-huh.
have this initiation in the weld, and it's going to generally propagate throughout the entire longitudinal axis of the weld. If the load level is a little bit less, if depending on
Uh-huh.
the load amplitude, actually the weld, it might start to fail through the weld, and then bending in the actual member, in this bottom member, it will bend and turn and actually fail this direction. From what I'm understanding, the initiation regime is kind of what you're most interested in, so the short crack growth, but we're characterizing kind of an entire failure through this type of image. So to answer your question in more short terms, it depends on the load level. This particular one initiated at the weld at 4 kilonewtons of peak load.
So did you see crack initiation on the base material itself for any of the cases?
Not yet. No.
Okay, so everything was for this 590. Everything the weld failed.
Correct.
None of the base material. Okay.
Correct. I do have some
Okay.
supplemental slides. We can look at a few different failures if you like, but as of right now, the weld is what is failing. The way it's
Okay.
failing, eventually, the initiation always happens in the weld so far. Like I said, in the maybe 10 millimeter crack length, it might turn and into the member, and then the member will eventually fail. So that's a
Okay.
possibility too. But the initiation is always in the weld thus far,
Okay.
which
Okay.
kind of makes sense just because the highest stress concentration is right at the tip here at the edge. Um,
Hmm.
okay, we'll go to the
So
next slide.
this is which thickness combination 590, and which is the thickness combination you are doing here?
Give me 1 second and I will check for you. Off the
Yeah.
top of my head, I can't exactly remember. It is a T-weld configuration with 2.6, 2.6, and it's 590.
Okay.
So I would imagine
Yeah.
with
Okay.
the top sheet thickness of 1.0 or 0.7, it probably will, it might start transitioning to the top sheet.
Yeah. So typically we see, we are expecting to see the crack on that, plate which you are bolting, since it is a higher thickness. Uh, yeah, that may be the case. Yeah. Got it. Yeah.
Okay. So I
Yeah, but
think,
but as Andrew said, so far all crack initiation has happened in the weld. But depending on the load level, as Andrew was saying, the final fracture may be all through the weld or may be transferred to the sheet. But that's
Okay.
way beyond the 2 millimeter crack that we are considering in this case, which is the size of crack that we are interested in terms of initiation life.
Mm.
Would that
correct.
happen in other cases? We'll do the test and we'll see whether that remains the same or not. But so far, all the crack initiation has generated from that root of the weld.
Yeah, okay. Yeah, in the actual parts, typically we see maybe this is a high strength material. That's why we typically see on the base material itself.
So that,
Yeah, when you do the 270, you may see a different case. That's what I am expecting.
yeah. So the crack actually initiates on the plate at the toe.
I mean, yeah, correct, exactly, on the plate at the top.
Okay.
May I ask a quick question? Because I don't know if I received the information. Is the filler metal that's being used, is that the same grade of, is it also 590 or it's a different alloy?
It's typically 440. It's a different
Okay,
grade.
that makes more sense than what you were saying, that if the member strengths are a lot lower, then you might see member failure. But if you're using 440 filler metal, then what we're observing here makes sense.
Okay.
But as Professor Jahed mentioned, I 100% agree with the fact that in this particular thickness combination, this is what's occurring, but we'll let you know as soon as we test the other configurations. And just to follow
Okay,
up,
so
I
then,
guess.
once this is done, can you show me go back to the other combinations, the thickness combination slides,
Sure.
the slide which are here.
The, okay, give me 1 second. Are you able to see this here? Oh,
It's not
sorry.
coming up yet.
Can you see this now here?
Yeah, then right now you started with 590, right? With
Correct.
2.6, 2.6. So next, can you go to the? I cannot see the top of your sheet. Can you go a little bit up? I cannot see that.
Is that better?
Yeah. Okay. Yeah. Yeah.
Would you
Can
like
you
us?
do the 0.7 to 1.6
Okay, sure.
JAC to the 270C? Yeah.
Okay, not a problem. We can do that second.
Yeah. Yeah. So the problem is that if 590 is doing the weld is cracking, I'm sure 780 will do the same because 780 is the highest strength.
I agree. Yes.
Yeah. So the basic idea for us is to capture that the crack initiation on that on that plate itself, not on the weld.
Okay,
So
understood. That makes
if
sense.
yeah, so if for 590 all the samples are doing, maybe we may have to create the 780B one here. So recreate and ship you those with the different thicknesses.
Okay. If that
Yeah.
that makes sense. If you're trying to observe the failure in the member right adjacent to the toe of the weld, then those configurations make more sense to me as well.
Yeah, because that's what where we see cracks in the real part. So the goal is to mimic whatever happens on the the real part.
Okay. Any other questions?
So
I have
yeah,
one final slide here that we can look at. Um,
yep.
So
so
the
this,
size of John, the size of the real part, the two mating part, is it more like this 0.7 millimeter to 1?
Depends on the depends where on the vehicle is. If typically on the wide body, the thicknesses are a lot lower. But if it is used on suspension components like stamp dams or the subframe, it is more like 2.6.
Mm-hmm. And even in
590 stock.
and in 2.6, you have also seen the same sort of failure.
But again, the structure of the part will be different and the weld length will be lot longer. So it may not be 60 millimeter weld.
Okay.
You know what I mean? Yeah.
Okay.
So if the length of the weld is much longer, probably the weakest point may be the base material itself.
Okay.
So if let me know when you do the 0.7 to 1.6, at least on that, since the weld material is stronger than the base material itself, we should be able to see it on the base material, the crack initiation.
understood. So just a final slide here. This is what we're performing DIC measurements on the full field strain on the entire image that you see here. And we can actually provide, in this case, it's the axial strain in the crack opening direction. So this crack is a little longer than the threshold, but we've done this at specific intervals. I've just chosen this slide to present just because it's more obvious what we're looking at, because the crack's
Uh-huh.
slightly larger. But in general, what I'm thinking that you need is the strain in the region. When you use the lower strength member material, the crack will probably go up like this somehow, or it might branch depending on the low level. But in this region is where you need the strain, correct?
I
Can you
didn't
see
catch
the
that.
cursor? Maybe
Uh-huh.
see the cursor here. So you want it at the weld toe in the member, right adjacent to the weld toe, correct? Like here or
Yeah,
here.
that's what we are expecting to see the crack. And in your case of 0.7 to 1.6, we hope to see it on that 0.7 member, the
Okay,
top sheet.
perfect. Okay, understood. That makes sense. I agree. Okay, and we're doing that at the max and min load, just so you can characterize that. That would be um, closing the loop with your finite element model.
Yeah, correct. Yeah, because this modeling this weld is a tricky phenomena, and we make a lot of assumptions regarding the weld, and the real part, again, the base material is the one which is going to fail. So we always focus on the base material.
Okay, understood. And with that, yeah, that's all the update slides I have to present. So if you have any more questions other than we would discuss right here, I would happily answer them via email. If Professor Jahed or Bezad will forward them to me. So
Okay.
just let me know.
Yeah. So yeah. So 590, all the testing is done. Is it? You finished all the testing.
As of right now, most of it is done for 590. We have a few more samples left to go, though.
Okay. Yeah, just hold off on to that one for now. Yeah, you can go to the 270 with
270.
the 0.7 to 1.6, and let me know your initial, initial results.
Okay, I agree with that because as I mentioned previously, the 590 samples, all I've observed yet so far is crack initiations in the weld. So
Okay.
that if that's not what you're looking for, then we need to lower the strength of the member material, as you mentioned.
Yeah, then yeah, we may have to. I'm pretty sure that 780 will do the same thing, so we may have to revisit that. So
Okay, understood.
yeah, yeah.
Okay. Um, so as far as residual stress measurement, I think the point that Andrew was showing at the weld toe for strain measurement is actually where we would like to measure the residual stress at. Um, and since we have two of those points per each sample, it would make sense that we make a measurement at each of the sides of this weld toe
Yeah,
at the
and
corner,
probably one in the middle.
and probably one in the middle.
Yeah.
Yeah, I mean, that's of course doable. Would you, just for the sake of repeatability and making sure that we get close answer in terms of similar samples. We are thinking of doing measurement on two separate samples per batch at the same locations, just to give a better idea of the ranges that we are dealing with. And later on for comparison that you're doing with your finite element.
So you want to do two per? Okay, yeah, that's fine too.
Yeah, I mean, you would like to have more measurement for different samples because we are assuming that they would be under the same condition and therefore would have the same state of residual stress. But of course, you would never get the same state of residual stress because of the local conditions that we have in each of these. So it
But
would be wise to
if you take three measurements on the same sample, that should give us some indication, right? So at the
well, of
two ends.
course. Yeah. Yeah, of course, that would be much better because then we would have an average and the max and a mean to work with in terms of the range of the values that we are getting.
Yeah,
Exactly those.
so yeah, that's what we are thinking of for doing only one because and this even that data is available, you won't be able to use in any of our models. That's the only reason we thought of going with only one sample.
Okay. So would you like us to just do on one sample?
One sample is fine. Yeah, one sample and three measurements
One
on one
sample
sample.
at three different points. Okay.
Yeah, correct. Yeah.
Okay.
So it just gives us a some feel of what is the residual stresses are. That's the whole reason.
Okay. Sure. Okay. If there's no question, then we can talk about the bolt testings that you
Yeah.
would
So
probably give us some more background.
yeah. So do you have some information to share or regarding the hardness? The hardening of the bolts once you machine it. Hello.
Hi, are you talking to me?
Yeah.
Well, no. Actually, we don't have any thing to share in terms of that, but we would like to know the size of the bolts that you are going to send, and
Okay.
if you have any idea of what the hardness would be after case hardening. I mean, the ones that you already have, or if you have some case hardened one, we can do some measurement in terms of the hardness on them, and quickly talk about the type of samples that we can machine out of that. The case hardening can happen afterwards. We can do it here locally. And the preloads that you're talking about, do you have any idea of what those preloads are, and the level of highest load that you envision in the test, or would that be most of most similar to what you're doing in other cases to get a range of lives after testing?
Yeah, the idea is to, it's a, general question, just to understand what case hardening does to the base material properties. That's the whole idea of what we are thinking about. So
What is
one
the
is the strength. We have got many areas, many components in these suspension systems are case hardened. So we don't have a feel for, what this case hardening does to the, especially in a strength scenario.
Okay.
So which material properties should we use in our final element model? Should we go with the case hardened material properties, or should we go with the base material properties, especially for a, strength simulations, not the fatigue, but the strength.
Okay. Okay. Now, the original material, what type of material are we talking about? Is that a material that we do have the properties already before case hardening?
No, we don't have. So basically, we need to do a, standard strength test with and without case hardening on a couple of samples, say.
Okay. Okay. And you want cyclic tests as well?
Cyclic test, we know for fatigue, we are very clear that, case hardening, fatigue cracks always go, initiates on the surfaces, and the case hardened properties we should be using. So the fatigue test should be done with the case hardened the samples.
Okay.
So the additional test which we need to request is the strength test with and without case hardening. That will give an indication of what should be used.
Mm-hmm. And those are quasi-static tests that you want to be done.
Yeah.
So doing quasi-static tests on as received material, and the same on the case hardened material, to just have a comparison between the properties of the two.
Yeah. The as received material, the bolt, when it comes to you, it will be already case hardened. So when you machine it out, that will be removed because it will be only few microns right on the surface.
Right.
When you machine the sample. So I can give you a specification of the hardness, and it is few microns on the surface. I can give you the spec on that.
Yeah, I think that spec is important to know, first of all, for machining purposes, and then secondly, for knowing what would be the type of hardness we are dealing with after case hardening for the test. And in terms of properties, you want just the regular elongation, ultimate value, and things like that.
Yeah. For strength, I would need, we would need both the with and without case hardening, and for fatigue, we only need the case hardened.
For fatigue, only the case hardened. I see. Okay.
Yeah, because you expect the crack to always initiate on the surface.
Sure.
So yeah.
Now, have you done any residual stress measurement after case hardening, or?
No.
So one of the things that happens for sure is that you will be inducing some residual stresses, because this case hardening is a surface type of treatment, and therefore the properties at the core is a bit different from the properties at the surface, and because of that difference in properties, you will get an interaction between the two to generate some internal stresses, which for fatigue is very important. I don't think they would play a big role in static loading, but for fatigue, it does. Not that it would change the way it behaves in terms of cracking from the surface, but it would sure impede or delay crack initiation.
Oh, okay. So it will only help us, right? So typically it is going to help us, all right?
Yeah.
It should have a positive effect on the fatigue life.
That should be what one would expect from getting that case hardening.
Okay. Yeah, then it's just to get a we won't be able to include that in our models anyway. So just to get a feel of that, we can do on a couple of cases.
Yeah, I mean, one sample I think would be enough after case hardening. Do a couple of measurements on one sample, and you will have an idea of. You're not talking about getting the distribution of residual stress near the surface. It's just the value at the surface for now.
Yeah.
Okay. Okay. Do you have your samples ready?
Not yet. So it will be typically M14 or M16 bolts. So I should be able to ship you that along the longer ones which we have.
Okay.
Typically what comes from the supplier.
Okay.
So,
okay. Thank you.
it will take, I just want to make sure that, you can do the case. How do you do the case hardening there at your end? Is it by heat treatment or?
Yes, heat treatment, and it would be done at a local facility in town.
Okay.
So our machine shop has done that before with this local facility. So that shouldn't be any problem.
Yeah, so I was not sure that you would be able to do it. So just wanted to confirm with you that you can do it. So
yeah, I think best talk to our machine shop, and they confirmed that this is doable, and they have done that before.
okay.
Best, am I correct?
Yes, that's correct.
Yeah.
Just a quick question.
Yeah, and then I should be able to get you. I need some time to get all the material ready and ship it to you, the bolt.
Okay.
Yeah.
Just a quick question. You mentioned there are M14 to M16 bolts. Is it for suspension, or is it for like the cylinder head of the engine? Are they torque to yield fasteners?
It is suspension.
Suspension.
It is suspension bolts. Yeah,
so
suspension.
They're not torque to yield.
Sometimes Honda doesn't do that. So it is. It will be it won't be from a vehicle, so it will be in a fresh bolt, so it won't have any preload or anything into it.
Okay, understood.
But
so
for
it typically goes from a arm to the subframe. That is the bigger size bolt.
Okay.
But for fatigue testing, you would like to have that mean load on it when we are doing cyclic tests, right?
No, I don't think so. We need that for the fatigue loading.
Okay.
It
So you
gives,
want
yeah,
fully
just a
reversed.
standard. Yeah, just a
Yeah.
standard
So you
fatigue
want the
test.
properties actually of that case hardened.
Yeah.
Okay. Okay. That makes sense.
Yeah.
Sure. Sure. Did you want me to send you a code on that then?
Yeah, that will be great. Yeah, just for this case hardening, I don't know right how much it is going to be, so I need to get an idea.
So I'll wait for you till you tell me you need a quote, and then I'll send you a quote.
No, you can send me the code. That's
Okay.
not a big issue. Yeah.
Do you want me to add this residual stress measurement on this MIG somehow in that code as well?
Yeah, maybe for 1 or 2 samples. We don't need for too many.
1 or 2 condition, you mean?
Yeah.
Okay, sure. So let's do it on 2 conditions. One, the one that we have already done the test, the 2.7 was it, right, Andrew?
Correct.
The 2.7 to 2.7, and then the
Yep.
one
Yep.
which is 0.7 to 1.6.
Yeah.
Okay.
So whenever you have the results for the initial results for the 0.7 to 1.6, please let me know. I just want to make sure that the crack initiates on the base material. Otherwise, we have to revisit the samples.
Okay, not a
Okay.
problem. We'll
Okay.
prioritize that.
So you want us to get some result on that 0.7 and share it with you before proceeding to the rest of the test.
Yeah, correct. Yeah, this 2.6 590B, you can stop it down because we once we show the results, then since the cracks are initiating on the weld itself, we may have to do something about it. Yeah.
Okay. Okay. Sounds good.
Yes. Yeah.
Any other thing that you want to discuss?
Yeah, we may have to do, there may be some other materials for fatigue, which is standard materials, is used in the engine mounts. That also maybe we may be doing this year. So
Okay.
yeah, we need some more time to get information regarding that.
Sure.
Yeah, on the other part, you helped regarding the damper housing. As I told that parts were completely out of spec because of the inclusion. When
Yeah.
the supplier did the CT scan, they found very large inclusions inside that casting. And they determined that was the reason one side was failing and the other side was not.
Ah, I see. Okay.
So it was made in a different die. There, because of the some minor changes, they have to make the left side part in a different die and the right side part in a different die. And one of them, because of some misalignment, there were very large inclusions inside the casting.
I see.
So they
Okay.
determined when I informed you last time, they went to the CT scan. So during the CT scan process, they found out that.
Okay. Okay. So the problem solved. At least you know where the problem is coming from.
Yeah. So then people here decided that since no point in testing something which is out of spec because anyway we are going to reject it. So
Yeah, that makes sense. Sure.
yeah.
Yeah. Okay.
Yeah.
So,
How is
John,
everything going?
the plan for testing the bolts, just to confirm, is to do static testing on non-hardened and case-hardened samples, maybe 5 of each, and then
3 of each is fine. 3 is fine. You
yeah,
typically do 3, right? 3 of each is fine for the static strength.
sure. And
And
then,
MIG, whatever standard you follow is fine. Whatever you have been doing, how many number of tests you do for all the other things is fine.
okay, you need a full strain life curve.
Correct. Yeah. Yeah. For the case hardened one. Yeah.
Okay, and you need some residual stress measurement, and do you need hardness test as well?
Not really. We don't need
Okay.
the hardness test.
Okay. Okay. Thank you.
Yeah.
Okay. Any other thing?
Yeah, that's it from my side, Professor Jahid. So thank you very much for all your help, especially during this time. Yeah.
Not a problem. Are you guys back to facilities, or you're still working remotely?
Most of us are working remotely. People who are in the test, they are going there and to make the environment more safe for the people who can work from home are still working from home.
I see. Okay. Okay.
Yeah.
Keep safe wherever you are.
Yeah, that's all. Yeah, even for the kids, school started, they are also online. So everything is
Oh.
online now.
Oh yeah. Okay. They
Yeah.
didn't actually start in some states. They are starting in person, I guess.
Uh, but who are started, they ran into so much trouble. So everything, they are pushing back to online now.
Yeah. Yeah. It's
So
probably
it
wise
is, it
decision.
is it is up to the parents. At least here they all gave the option to the parents whether to keep the kids in school or send them back to school. Even if you opt them to send them back to school, they can go to school only 1 or 2 days a week because they
Uh,
can accept only 25% of the students.
I see. More or less the same here. In Ontario, they're asking parents right now. I think they had up to 3 days ago or last Friday to tell the school whether they're willing to send their kids back to school or they want to use the online option. And apparently, majority of them decided to. The actual stats is not out yet, or I'm not aware of it. It might be, but it was that most of parents are choosing not to send their the kids to school.
Yeah, same here.
Yeah.
So how about the university? Is it all online or is it in person also?
Well, I mean, practically it's online, but
Okay.
but we have something around 400 students on campus, which will still be attending online classes. But would have areas for studies and things like that, and they will be living on campus. So there are some sort of students that we normally would have something around 20,000 in fall term. So 400 is just nothing, as compared to that.
Yeah,
Um,
right.
but the university is pushing very hard to have a minimum amount of in-person session, especially for lab experience. For some of the courses that there is no escape now, and you can't do the lab in any other way. And those are very, very limited. Maybe a handful number of occasions or cases. And that's
Okay.
mainly for saying that we are gradually coming back to
Sorry.
normal. But practically, still everything would remain online.
Okay.
I tried this in the first name, but
Labs are open. I mean, research labs are open. Operative, and as Andrew was saying, there are lots of restriction, and there are safety guidelines that we all follow. So lab use is
time's
now
up.
very limited. We can't get there earlier than 8, and we need to be out before 5, and no weekend type of
What?
going in and setting up any tests. Now, in our cases, as Andrew was
My
saying,
computer will work.
he has to do lots of trial and error and planning to make sure that Friday, when he sets up a test before leaving, it will run over the weekend, so he use up the machine to its limit. But research labs are, I think all of them are now open or will be open by this week, all of them.
Okay.
And so the activity in terms of research, especially experimental work, has come back to not the same level that it used to be because of the restrictions, but I would say more than 50-60% back up and running.
Yeah. At least the labs are running. That's good for the students. They won't be delayed with their masters and PhD.
Yeah. I think graduate students are very active and have remained active. And coming fall term, there will be the main activity on campus will be them that would do their lab work. Limited use of offices is still allowed. So that would be the main traffic and activity that is on campus happening. The online version of courses, of course, people are wherever they are. Um, and there won't be any in-class session. That might be one or two. They are saying that two grad courses, I think, not in our department though, will be in person. And that's a course with 10 students, which are spread in a classroom of a size of 100. So they're really spread out, and they would have in-class lecture. As I said, it's mainly for the sake of having it, as opposed to not having it, just to pave the way for returning back to in-person sessions in future, which we don't know when that future would be.
Yeah.
Pretty unprecedented times.
Yeah, thanks. Yeah.
Okay, then. Any other thing, John?
Yeah, that's all. Yeah, just staying home. What else you can say?
Yeah. Okay, guys. So take care and keep safe. And we'll update you as soon as we have new updates.
Yeah. Yeah. Thank you very much for your help.
Okay, thank you. Andrew and Behzad, can you remain so we can arrange for what we just discussed?
Yeah, sure.
Sure.
Okay.
Yeah.
Okay,
Thank you,
take care,
brother.
John.
Yeah.
Take care,
Thank you,
Pravin.
Andrew. Yeah, thank you,
You're
brother.
very welcome.
Bye.
Yeah.
Bye.
Yeah.